Before you close off this video, have you ever been in this kind of situation before?
Hello students, welcome to the calculus course. Today we're going to talk about the definition
A few moments later.
integral of y1 to the negative 2 e to the negative integral of.
If you have been in these situations, then welcome to the first episode of our series called Calculus for Dumb Babies. In this video, I aim to teach you guys about calculus in a way that is intuitive and easy to follow. So whether you are just like a primary student who are interested in this subject, or maybe you are someone who maybe have graduated but haven't really touched calculus in a while and wants to revisit the amazing idea, the fascinating branch of ideas that calculus originates. So, without further ranting, let us begin with how calculus actually originates and the main ideas behind calculus. 3, 2, 1, go! Before we really dive into the creation of calculus, we have to really know like where like the origin of calculus actually appears in the discovery of mathematics. So let me bring you all back to the ancient Greeks. So I think you all would recognize these three guys, right? Socrates, Plato, and Aristotle. So pretty much they are the face of Greek philosophers, which is really a subject of questioning pretty much everything you see. For instance, who am I? Why we are doing this? What is love? Why are we born? Is God real or something like that? That is the subject of philosophy. I think they are just bored, I guess. Probably at the time there's no Netflix, there's no K-dramas, and there's no no games to play. So basically what they do it during their bored and make a study around 2000 years later. Anyway, okay, so they study about philosophy. And by extension, philosophy is this science and math just in its youngest form, right? Because in philosophy, we questions like how things occur and all that. And we do that similarly with science and math. Just for science, it's just kind of like the nature around us. And for math, it's maybe like the patterns we see around us. So basically, the topic of philosophy actually gave rise to what we call natural philosophy, which is literally the philosophy of things around us, aka science and math. So at the time, some of the common natural philosophies are cosmology, like looking at the stars, astronomy, or something like that. Elemental theory, you might have recognized as like maybe fire, earth, water elements, how they influence our bodies and something like that. And the next set is maybe like the logic, how we think and how we process information, I guess. That's how to phrase it. But the one important thing I want to note is geometry. So, geometry, at the time, it was mostly what we call Euclidean geometry. And basically, Euclidean geometry is what you learn during middle school. For example, how lines intersect each other, inscribed in like the square and all that, and you have to determine length. For example, lambda in this figure, what is it? In maybe do some angle, like this is a right angle or something like that. That is what we call Euclidean geometry, and it's a geometry that the Greeks are just kind of exploring at the time. The point is that they want to study about geometry, and the reason being is that geometry is literally all around us. So if you're watching from iPhone, iPad, or laptop or something like that, the shape of the monitor, right, the things we are actually looking at, is actually a rectangle, you know, and maybe a lot of things like maybe this cup, this cup here is actually a circle, you know, the circle around here. So basically, geometry is all around us. And that's why the Greeks just kind of want to notice the patterns and what's going on with this kind of thing. So these are some of the common shapes the Greeks study. So of course, squares, rectangles, triangles, and circles, which are common around us. And one thing they like to do is to find the area of the square. So if you have taken some of the geometry class in middle school, or maybe I think some primary school also study the geometry. So basically, to find an area of a square. So basically, if this side is maybe, I'll denote it as a letter A. A can represent any of like the length, for example, 1 or 2 or 3 and so on. I just want to denote it as a single letter for simplicity, you know? And for example, if this side, since this is a square, this side is also A, which can be like 1 or 2 or 3 and so on. The area of this area, which is equals to these two sides times together. And so we can write it as A squared. Squared being that there are two A's, two, how should I write this? Two A's, S. Okay, so basically there's two A's, so we write it as A squared, like this notation right here. Okay, so so it's not that hard to find the area of a square or rectangle by extension if this one is not equals to A. For a triangle is also kind of simple. So if you have learned, you may know that the area formula for a rectangle, no, sorry, for a triangle is actually if this has the height of h, just a simple letter that just denotes the height. You can find, and this, for example, its a base is length b, where b is just again another letter. We just denote these lengths with a letter to make it looks good. We can find the area of a rectangle to be 1/2 b and h. It's simple as that. And if you're just curious about proof, you can look it up online. It's not that difficult. But what is difficult is this thing right here. Circle. You see circle everywhere, but Greeks struggle to find the area of a circle. Partly it's because like this has like 4 sides, right? This one has 3 sides, and this, well, there isn't really any sides, and it's not that obvious for you to find the area of it. So the Greeks, one of the natural philosopher that his name is Archimedes, actually came up with a very clever but also kind of controversial solution at the time. So we're going to be discuss that, and we'll see how the main concept of calculus actually originates from that point. Okay, so circle. Archimedes said that, what if we try to find the area of the small pieces instead? So what he means by that is, there's a circle, right? So why don't we try to divide it somehow, and maybe try to find the area of the small pieces, and then just kind of add them up together again. That may be an easier approach, and the approach he came up with is actually very clever. So you all know about pizza, don't you, right? You eat it all the time, especially in my country. A lot of people just kind of eat pizza during maybe celebration or something like that. I think that also applies to other countries as well. But okay, let's just get back to the point. So basically what we do is we have a circle here. So let's divide it into like a pizza slices, 8 slices. So what I mean is something like this. So this is 4 slices, and then we divide it into 8 slices. Let's do this instead. All right? Cool. So with these 8 slices, we can see that there are just kind of these wedges right here, right? These slices. And what Archimedes suggests is if we rearrange these wedges into a shape that maybe makes it easier for us to compute the area. So one of the shapes he did is rectangle, right? So we can rearrange this into a shape that just kind of looks like a rectangle. How do we do that? Well, we can do something like this. We can do something like this, like this. So this is size 1. So 1 is just kind of something here. We just kind of transfer it over here. 2 is maybe the same, and then we transfer it over here, and 3, and so on. So if we do this, I'm just gonna draw it real quick. This is 4, 5, 3, 4, 5, 6, 7, 8. 6, 7, and an 8. There we go. You can get the sense that this shape is not really a perfect rectangle, but it looks kind of like a rectangle, don't it? Like, this is actually looks really like a rectangle. And if you guys kind of see, if we actually make the slice a bit more precise, then we might actually get a shape that actually looks more like a rectangle. So, well, that's what Archimedes did. So this one is a kind of like a drawing, and I'm not really good at art. So I actually made it in Python, and this is what it actually looks like. So for 8 slices, we get a shape that kind of looks like a rectangle, but it's not exact. For 16 slices meaning we slice this pizza even further. So basically, we just slice this even further, like this, like this. Yeah, we just slice further. We will get a shape that looks even more like a rectangle, don't it? And if we do 32 slices, which is literally just like a double of what we already have, like we can insert a line between here, between here, between here, and we actually got a shape that looks even more like a rectangle, but it's still not really a perfect fit. But what you can notice from now on is it actually made the number of slices much, 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 much higher than we might actually get a perfect shape. So technically, if we make the slice very, 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 very large, if large to like infinity, we might be able to get the perfect area. And that is actually the case, because if we make these slices like infinitely many, we then get the shape that looks exactly like a rectangle. Like at first you might thought that having more and more slices just kind of makes your job much harder, but it actually makes a really nice rectangle. And if we denote the radius, which essentially radius is just the length between the center of the circle to its kind of like outer shell, we denote this as R. So basically, R is just a simple letter we denote this. Then you can notice that the sides of here is actually R, right? Because this one side here is a wedge, and if the wedge is kind of stacked together, it's going to form this one, going to be our radius. Now, if we look at this side again, you can see that these two sides is actually like this two side actually forms like the entire length of the circle, right? You see, if these two sides are these outer far sides of the rectangle actually is like the circumference, which is like a technical word for like the distance of like the entire circle. So this thing is actually the same. So very basically, like if this one is length 1, this would be 1/2, and this would be 1/2. And so we can know that if there's infinitely many slices, then the side here is going to be half of the circumference, right? The circumference, mind you, is just literally like the kind of like the shaded length here. This is like the circumference, and from you might know that this circumference is actually equals to 2 times a constant called pi, which is a constant that just kind of signifies like the circumference divided by the diameter. It's a constant, and it's just a value like 3.14, etc. And then times r. So essentially, this one here is actually equals to 1/2 times 2 pi r, which is the circumference here. And that we can say, okay, 2 divided by 2, that should cancel, and that results in pi r. Good? Good so far? Okay, so how do we find the area then? Well, since this rectangle is exactly the same as the circle, the area is simply r times pi r, and that is pi r squared. And if you remember, pi r squared is indeed the solution to the area of a circle. Okay, still following? It's a bit difficult here, but I'll recap here that what we essentially did is we have a circle, right? It's really difficult for us to find the area of the circle directly. So what we do is we slice it up into tiny bits, like tiny wedges, and then we stack them together just like this. We stack them together, and we found that if we can continue to increase the number of this kind of wedges, it's going to eventually approach the shape of a rectangle. And so by computing the area of this rectangle, we are essentially computing the area of the circle. It's the same thing. And that's how we arrive at this area of a circle. Okay, so now let's look at a slightly different story. So I think you all have been on a car, right? I think, well, or maybe not on a car, maybe on a bus or something like that, but I think you have all experienced going on a sort of vehicle before, something like this, right? It's really cute. And yeah, family road trip. Okay, so yeah, that's pretty much my face when I go for a family road trip. Okay, so let's don't get too much out of the story. So if you've been in a car before, you would probably know that there's this kind of speed meter, right? On like your dad's kind of riding, when your dad's kind of driving the car, there's this speed meter, and it just display the speed at time. For example, at the start, the car is zero, speed is zero, but when you move, your dad push the acceleration, it's going to increase to a level, and when he just kind of slows down, the speed just goes 0 to 0 and all that. And yeah, that's actually just denotes the speed. This meter actually just shows you the speed in kilometers per hour. But what exactly is a speed? Well, the speed is this one here. It's basically just like the change in distance in the units of kilometers and divided by the change in time of unit hours, right? So something like this. But you may notice something a bit off from what I said. The definition of speed is the change in distance and divided by the change in time. So change means there must be 2 points, right? In order to determine change. For example, if you just kind of look at me right now and look at the only frame, you cannot really know which side am I going to continue to moving. For example, I can move this side or this side at different speeds, and you can really know that if you just look at an instance. But that is exactly what you see in a speed meter. Like the speed meter, when you're that, it shows like every instant of the speed. But technically, you can't really have an instant of the speed because the speed is literally defined as a change in distance. It sounds, it's really paradoxical, isn't it? But you know, how does your car overcome this paradox of, you know, meaning? Well, it's actually performed a very cool technique, which I'm going to show you next slide. So basically, this is like the graph of the distance in kilometers and the time in hours. And since the definition of speed, we can know that the speed, of course, the speed in this case is going to be the change in y divided by the change in x. That's literally the same definition as before, just rewrites in the context of this graph. We're good? Okay, and this graph is actually very interesting because the distance is actually equals to time squared. Time squared meaning that time just kind of times itself again. All right? So if, for example, if we want to know the exact time at 3, how do we do? Now, let's just determine like the speed between maybe like the points, the time equals 2, and maybe the time equals 4, right? So since this is like a distance equal time square, so basically the time at 2, there will be the distance of 2 squared, which equals 2 and 4 in like the coordinate plane, you know, the point 2, 4. And for this one here, since the time is 4, then the distance will also be 4 squared, which is 4 times 4, which equals to 16. There we go. So we can determine the speed of this interval over here. So we can speed equals to, of course, we have to take 16, the change in y, right? 16 and change mean minus. So change minus 16 minus 4 divided by 4 minus 2. That is our speed of this interval. But what's the technique is this? So this is like a range interval, right? But if we want to measure the exact speed, for example, at time equals 3, then why don't we just make the interval very, 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 very small and then measure the speed from that interval? So what I mean is this. Let's assume that the tiny step in time that I'm going to make is denoted as the letter H, right? So I just want to use this symbol. So basically, if I just move little in time, little, this is like maybe a bit kind of over exaggerated, but what I do is like zero point 0.1 hours, 0.01 hours, or something like that. That's like a tiny step forward. All right. So what do we have in the speed? Well, what we have here is that it's going to be the distance at which this move like plus h and then minus by the distance at times equals 3. So that's going to be 3 plus h squared, because this is like the definition we're actually working with distance. So it's going to be 3 plus h squared minus 3 squared divided by 3 plus h minus 3. So this is going to be the equation for speed. And remember that h is very, very small. So I just write note here. Very small. What we get from here is that we see 3 minus 3 is 0, right? So basically, only h remains in the bottom. And from the above, we can expand this. So we can expand this further. That's going to be 3 squared plus 2 times 3 times h plus h squared minus 3 squared divided by, since h only remains, we got h. And this expansion, if you just like, what on earth is this expansion? Well, it's algebra. You can try to do this. You can try to times 3 plus h times 3 plus h, and that will actually give you this result. All right. Now we can cancel this too, right? Because 3 squared minus 3 squared is of course 0. So this term is eliminated. And you see, there's h here, right? And there's h here, and this divided by h. So basically, h divided by h is of course 1, and so these two actually cancel. H squared divided by h is, well, h. Remember that h squared is actually h times h. So basically, 1h is cancelled. And so what we remain from this expression is just 2 times 3 plus h, or basically 6 plus h. Remember that 2 times 3 is equals to 6. But notice that we said earlier that h is very small. And so technically, if h is really small, we can just kind of neglect it. We can say that the speed is 6, right? Because the h is actually really small, so basically we can just ignore it. And so our speed is just 6. That's how your car actually displays the speed. And that's really cool, isn't it? That's really magic. So with this two example, the example of the area of the circle and the motion I've shown you here, notice the subtle nuance of these two examples. We are dealing with something that infinitely small. For example, in the area of the circle, we are dealing with very, very small slices of pizza, and we just rearrange it and we sum all of them together. For the speed here, what we're doing is actually we just chop it into a very small step in time and then measuring the very, very, very small change. That's pretty much the two major ideas we found in calculus. For area of the circle, this is really the fundamental idea of what we will explore later in the series called integrals or integration. And for this speed meter, this is literally the fundamental idea of what we call differential. And literally, calculus is about exploring the properties and the relationship between differential and integration, which is the operation that just kind of focus on something very, 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 very tiny. All right, so that's really like the whole concept of calculus summarized in this 20 minutes or something like that. One thing you should note is that I talk about like very, 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 very small, right? But in order to make it like that kind of saying well defined in mathematical terms, we actually need to learn another tool, which is going to be the subject of the next video in this series. That tool is what we call limits. And With this limit, we will be able to define this kind of action of cutting into very small things and then summing up together, which is integration, and then cutting like a very small time step and measuring the change, which is differential. Limits is what allows you to kind of properly define these two operations mathematically. And yeah, that's pretty much the whole picture of calculus. If you have listened to this far and still kind of understand everything, congratulations, you have finished 2 semesters of calculus word of content. Well, just kidding. But the main idea is this, and if you understand this main idea, I'm guaranteed you will have a much easier life when trying to understand the different concepts that will be explored later, or the things that you are actually learning in the course, like maybe in the university or something like that. So, congratulations for making it to the end. And if you made it this far, don't forget to give me a like, subscribe, and comments. I'm still like a growing channel, so if you just kind of comments and hit a like button, I really appreciate it. I do read every comments that you posted, and if I rate it, I will give you a heart. So yeah, thank you so much for watching it, and I hope you stay tuned for the next video, which probably going to come out in the next few days from now on. All right, so yeah, that's pretty much it. Thank you so much for watching. My name is Ken. I hope you have a great day and see you next time. Bye bye.